Bismillahirrahmanirrahim. Assalamu alaikum. How are you, dear students? Today we will discuss topic from course Inorganic Material Chemistry, and course code is CAM 3115. Topic that we will discuss is properties of advanced materials. In previous lecture, we discussed mechanical properties of advanced materials, and today our topic is electrical properties. Let's start our discussion. So in this lecture, contents that we will discuss. First, our main topic is electrical properties of advanced materials. So in electrical properties, when we talk about electrical properties, then these are related to electricity or electrical conductivity. So first, we will talk about electrical conductivity, and then we will discuss about conductivity and resistivity, what is difference between them. And next we will discuss electrical properties of materials, on which kind of or what we can study in if we are studying electrical properties of materials. Then we will discuss the types of materials that may be conductors, semiconductors or insulators, and later we will discuss their detail. The next thing that we will discuss under the electrical properties of materials, on which these are based, are electrical conduction or band gaps. And in electrical conduction and band gaps, we will discuss about types of band gaps and mechanism of electrical conduction. Then we will discuss semiconductivity, and in semiconductivity we will discuss doping, and that may be intrinsic semiconductivity or that can be extrinsic semiconductivity. And later on we will under this topic semiconductivity, we will discuss the applications of semiconductors, how we can modify our materials and we can apply them in different micro electronics. Next we will discuss in electrical properties of materials, we will discuss effect of temperature on conduction. And the final thing that we will discuss is superconductivity, and we will discuss how we can make superconductors, how we can modify materials into superconductors, and their applications on applications of superconductors in electrical industry or microelectronics. So overall properties, electrical properties of advanced materials, we will discuss in our next lecture. Electrical properties of materials could be divided into three types on the basis of electrical conductivity. These include conductors, insulators, and semiconductors. And conductors are further divided into metallic conductors and electrolytic conductors. So mostly solids show electrical conductivities in the range of from 10 raised to power minus 20 to 10 raised to power 7 ohm per meter. As electrical properties are related with electrical conductivity, so we can say that materials which have capacity to conduct an electrical current, that are conductive, or they have electrical conductivity. So if electrical conductivity of material is greater, then we can say that it is easy to pass electricity through it. So any material from which electricity can be easily passed, that are known as conductors. So mostly metals are good conductors of electricity. Before going to discussion about conductors and other types, first we should know few terms, that is basic and important terms, that are conductivity and resistivity. So what is conductivity? Actually, conductivity is a measure of how easily electricity can flow from any material. So if electricity can pass easily from any material, then we can say that have more conductivity, or that material is more conductive, or that is conductive material. So what is electrical resistivity, or what is resistivity? Electrical resistivity measures how much a material resists the flow of electricity. We can say that conductivity and resistivity are opposite to each other. So these both are inversely proportional to each other. So we can say that when conductivity is lower, then resistivity will be higher. And the same way, when resistivity is lower, then conductivity will be higher. So if any material that have low resistivity, its conductance will be more. So we can explain this by this equation, that is equal to rho is equal to 1 over sigma. So resistivity is inversely proportional to conductivity, and similarly we can say that conductivity inversely proportional to resistivity. So we can represent resistivity by rho, and it is measured in ohms meter, and conductivity is denoted by sigma, and its units are Siemens, that is 1 over ohm meter. When we are going to discuss electrical properties of materials, then here we will discuss, I have told you that there are three types of on the basis of conductivity, that are insulators, conductors, and semiconductors, and other type that we will further discuss is the superconductors. And other important thing that we will discuss about energy band gaps. And further thing that we will discuss is in semiconductors is the doping, and that could be intrinsic and extrinsic doping. So conductors are that material which allow electric current to pass through them. So any material that allow electricity or electric current to pass through them are called conductors. So mostly conductors have conductivities in the range of 10 raised to the power 4 to 10 raised to the power 7 per ohm per meter. And metals, mostly metals have conductivity in the range of 10 raised to the power 7 ohm per meter. And metals are best conductors of electricity. So if we want to take example of conductors, then metals are good conductors of best conductors for electricity. And examples of conductors, metal conductors are copper, it could be silver, iron, etc. So metallic conductors that allow metallic conductors are those conductors which allow electricity to pass through them without undergoing any chemical change. In metallic conductors, no chemical change may occur, but it is due to that conductance is because of the movement of electrons that are present in that metals. So metals can conduct electricity in both forms. They can conduct electricity in solid form as well as in molten state. So this conductance in metals is due to the free movement of electrons, and this is without any chemical change in it. So example of metallic conductors is copper, silver, iron and gold, etc. So other type of conductors, we said that we can divide conductors into two types. One is metallic conductors and other is electrolytic conductors. In case of metallic conductors, the electricity can pass through that metallic conductors without any chemical change, and that electricity or that conductance is due to free movement of electrons. So in case of electrolytic conductors are those conductors which allow the electricity to pass through them by undergoing chemical change. Like in electrolytic conductors, some chemical change may occur and then they can allow electricity to pass through them. So this is also possible in ionic solids, like conductance in ionic solids is due to the movement of ions or other charged particles. So in this example, you can see in left side figure, you can see that ionic solids in solid state will not conduct electricity. But on the right side, you can see that these are in free form. These charges are in free form. So ionic solids can conduct electricity in molten state or in aqueous solution. For example, on the left side, you can see there are crystals or solid material for sodium chloride. Then it cannot conduct electricity because it is in packed form, and here charge cannot move freely. But in case of when you make a solution of that sodium chloride, then it will convert into ions and electricity can pass through them. So they are known as electrolytes or electrolytic conductors. So in left side figure, so on left side you can see that this ions are not free to move. These are in packed form, so electricity will not pass through ionic solids. But on the right side, you can see in figure that there are spaces between these ions and they can freely move. So this electricity can pass through them easily. So example of electrolytes other than ionic uh, these electrolytes are ionic solids is sodium chloride and potassium chloride. When these are in molten state or when these are in aqueous form, they can conduct electricity. So next type on the basis of conductivity that we explained previously is about insulators. So materials that do not allow the electricity to pass through them that are called insulators. So insulators have very low conductivities that are in the range of 10 raised to power minus 20 to 10 raised to power minus 10 per ohm per meter. So if we take examples of insulators from our daily life, then we can see glass, wood, plastic, ceramic, rubber, fabric, wool, or cork are examples of insulators. Electricity cannot pass through them, so they are examples of insulators. And from other materials, we can say that sulfur, phosphorus, or vanadium pentoxide are examples of insulators. So next type is semiconductors. So materials whose conductivity lies between metallic conductors and insulators that are called semiconductors. So we can say that semiconductors have conductivity between insulators and conductors. So their conductivities are in the range of 10 raised to power minus 6 to 10 raised to power 4 per ohm per meter. So examples of semiconductors are germanium, silicon. In this figure you can see that here are silicon chips, that is example of semiconductors. So electrical conduction, we can say that for electrical conduction the main source is source are electrons. So we can say that electrons are a major charge carriers which can conduct electricity. So in case of metals, we can divide into energy bands into three types. One is the core band, valence band, and conduction band. Here we will discuss these bands in detail. So a core band is that band in which electrons are not involved in bonding. So in our topic, we are considering electrical properties in which we consider conductors or conduction. So in case of conduction or conductor semiconductors, these two bands are involved. That one is valence band and another is conduction band. So a valence band involves it is outermost shell that comprises of valence electrons, and it has a lower energy than that of conduction band. And conduction band consists of free electrons that are responsible for conduction, and in metals and alloys mostly these free electrons are able to conduct electricity. So a valence and conduction band are two different energy levels that are separated by a certain amount of energy. There is an energy gap between valence band, valence band and conduction band, and that band is known as energy band gap. Next, I will show you these valence band and conduction band and mechanism of electrical conduction, and we will discuss energy band diagram, that how they lie, conduction band and valence band, how they are arranged, and what is in different conductors, semiconductors and insulator, what is the difference of this energy band gap between them, and how electrons can move from valence band to conduction band. So what is mechanism of electrical conduction? So there is a band model, as we explained that in electrical conduction we take two bands into consideration. One is conduction band and other is valence band. So in conduction band, and this is known as band model. So valence band is actually outermost filled energy band, and conduction band is empty energy band, or it can be partially filled band. So if there is when electron move from valence band to conduction band, then it needs some energy. So the distance between valence band and conduction band is known as energy gap. So when electron moves from valence band to conduction band, they have to overcome this energy gap. The distance between valence band and conduction band is known as energy gap. Here, conduction band may be fulfilled, or it may be empty, or it may be partially filled, and valence band is the outermost filled energy band. And so for metal conductors, semiconductors, and insulators, energy band could be like this. This is increasing order of energy. In case of metal conductors, you can see here, this is valence band and this is conduction band, and there is no energy gap between valence band and conduction band. So for electrons, it is easy to move from valence band to conduction band. In case of metal conductors, valence band may be energy gap between valence band and conduction band may be 0 or it may be very less. So energy gap here is 0 electron volt. Here no energy is required to jump electron from valence band to conduction band. In case of semiconductors, the semiconductors lies between metal conductors and insulators. Conductors are those materials which can pass electricity, and insulators are those materials from which electricity cannot pass. And semiconductors have characteristics between metal conductors and insulators. So in case of semiconductors, valence band and conduction band has energy gap. So as compared to metal conductors, their energy gap is bigger. So in case of semiconductors, in this case we can say that energy gap is 1 electron volt. So electron have to jump after getting energy of 1 electron volt. It can move to conduction band. So in case of insulators, here is a valence band, this is conduction band, and you can see that the difference between two bands is very large. Energy gap is very large. So in insulator, it is impossible for electrons to jump from valence band to conduction band. So in this case, much higher energy is required to jump from valence band to conduction band. So in this case, we can say that energy gap is about equal to 5 electron volt. So in case of metal conductors, this energy gap is 0 or it may be very less. In case of semiconductors, energy gap is smaller than insulators but larger than metal conductors. In case of insulator, this energy gap is very large. So it is difficult for electrons to move from valence band to conduction band. So conduction of electricity in semiconductors, mostly semiconductivity is found in transition metal compounds apart from metallic compounds or metallic metals. So silicon and germanium are most important examples of semiconductors. Silicon is mostly used in transistors and computer chips, and germanium is utilized in solar cells and for nanowires and other related materials. So, conductivities for semiconductors. These semiconductors are very low for practical applications, and mostly they behave as insulator because their conductivity is very low. So we can say that these materials, silicon and germanium, can behave as semiconductors in two ways. In one, we can say these are intrinsic conduction, and other way is extrinsic conduction. Intrinsic conduction, in case of intrinsic conduction, then increase in temperature can make it intrinsic conductors. And if we add some impurity and reduce doping, then it may show extrinsic conduction properties. So the ability to dope semiconductors, and if we modify them by increasing temperature or by adding some impurity, then we can modify their electrical properties, and which can be used in different applications, and these are the basis for microelectronic industry. As we discussed that intrinsic conduction is due to increase in temperature. Here we can see that this is a network of pure silicon, and if we want to increase its conductivity, we want to make it good conductors, then we will increase its temperature. And by increasing temperature, bonds will be unstable, and here bond will break. So when bond will break, the hole will produce here, and electrons, these holes, positive ions, will start to move in this direction, and electrons will start to move in opposite direction. So by increasing temperature for pure network of silicon, we can add some conductivity into that. But in case of intrinsic conduction, this is very low for practical applications. Next type that we discussed, that we said that in semiconductors we can add some, we can increase their, we can use them as extrinsic semiconductors. So extrinsic semiconduction is the addition of some impurities. So process for addition of impurities is called doping, and these impurities may be electron rich or electron donor species, which can provide electrons, and these impurities can also be electron deficient, which have electron deficiency and can accept electrons. So these two types of impurities could be added into semiconductors to make them extrinsic conductors. First, we will take example of electron-rich or donor impurities. Here we can see that group 14 elements are semiconductors, and here we take pure crystal of silicon. Here silicon, pure silicon is present. So these are 4 valence electrons elements that have 4 electrons in their valence shell. Here what we do, that we add impurity that is electron rich, that has one electron higher than this one. So this group 14 has 4 electrons in their outermost shell. So we will add that species which have 1 electron higher than this group 14. So we can add any elements from group 15 in which 5 valence electrons are present. So here we added arsenic. So 4 electrons can bond with silicon, but 1 electron will remain free. This is extra free electron, and this is in loose form that can move freely, so it will cause conduction of electricity. It will also cause electricity to pass, or it will increase conductance. So we can say that these electron rich donor or impurities are added in this silicon. Then these are N-type semiconductors, and N stands for negative or electrons. So for electron deficit or acceptor impurities, electron acceptors, we will add, like here you can see that the same like we add in previous, we add silicon, and here we take germanium. This is also from group 14 and it has 4 valence electrons. It can form 4 bonds with other germanium. So in this we have added 1 electron deficit species, the element. Here we can see that group that have 1 electron less than group 14 is group 13, and it has 3 valence electrons from group 13. So here we have taken indium and we add it into this germanium semiconductor. So when we will add this indium, then these 3 electrons can form bond with other germanium atoms, but 1 will remain empty. So here positive ion, that is known as hole, will produce. So no electrons are present here. So for electric conduction, there must be some holes, or there must be some negative ions, or there must be some positive holes. So then other electrons can move into this system. So here doping of indium, this is electron deficit species. So these type of semiconductors are known as p-type semiconductors, and P stands for positive hole, because here we instead of 1 germanium we added indium, that is electron that has 3 electrons in its valence shell. So when we modify these semiconductors with extrinsic properties and into extrinsic conductors or intrinsic conductors, mostly extrinsic properties, conduction properties are important for practical application. So we can use these semiconductors for different applications. So we can say that the main application of semiconductor is in solid state devices, which include transistors or silicon chips, or it may also include photocells. We can make these devices because the energies of electrons in highest occupied levels are different, and it depends on material is doped with N-type material or it is doped with P-type. So that material, such as if we use silicon and it is doped with a trivalent element, as I have discussed in previous slides, and when it is doped with trivalent element, we can say that it could be boron, So it will make p-type, or if we dope it with pentavalent element, that could be phosphorus, then we can make it as n-type. So these differently doped materials that may be p-type or n-type, they can show different properties, and due to this many microelectronic applications and microelectronic industry groomed. So in case of LEDs, we can take the example of LEDs in which gallium arsenide or gallium phosphide are used. So here you can consider that how you can convert these semiconductors, or how you can modify these semiconductors by doping it with different materials, with n-type or p-type materials, and you can enhance their electrical properties. So what could be effect of temperature on conductivity, are different types of conductors, insulators and semiconductors. So in case of metallic conductors, here you can see this is example for metallic conductors. So conductivity of metals decreases with increase in temperature. We can say that conductivity is inversely proportional to temperature. So if conductivity decreases with increase in temperature, that it shows that resistivity will be opposite. So in case of semiconductors, conductivity of semiconductor increases with increasing if we increase temperature, as we take example of intrinsic semiconduction. Here you can see. And in case of insulators, so very little increase in conductivity may occur with increase in temperature. In other cases, insulators cannot allow electricity to pass through them. But if we increase temperature, then little bit increase in conductivity may occur. So as we discussed that the conductivity decreases with increasing temperature. So many conductors have conductance, but it is not up to 100%. Like if you have a wire and you are supplying electricity is coming from any power station to your home, and you are using copper wire or brass wire, then total energy that is coming from powerhouse is 100 ampere, and energy that reached to your home is 80 ampere. So in other case, like if you have your neighbor that is using silver wire, and electricity that is coming from power house is 100 amperes, and that is reaching to your neighbor house about 90 amperes, and this 20 amperes or 10 amperes is lost because of resistivity. So in other cases, like you can say that another home in which electricity is coming from powerhouse, it is 100 ampere, and it reached to third home about 99%. So what is the difference between why at one place you are getting only 80%, 80 ampere, and other you are getting 90 ampere out of 100, and in third case you are getting 99 ampere out of 100 ampere. So actually what you can do that in first case, like if you are using copper or brass wire, so it is showing this conductivity is about 80% or 80 ampere electricity. Only 80% electricity is coming to your house, and if you want that your you can get 100% or 99% electricity, then what will you do? That you will take that brass or copper wire and you will decrease its temperature. You will lower the temperature at that range at which its resistivity will be 0 and conductance will be 100% or 99%. So these kind of materials which can conduct 100% electricity are called superconductors. So some metals lose their resistivity completely and at low temperatures, like it could be above 0 Kelvin. So at that temperature, if metals lose their resistivity and they are completely conductive, then this phenomena is called superconductivity, and that materials are known as superconductors. So the temperature at which that resistivity vanishes, that is known as critical transition temperature. You can say that temperature at which resistivity is 0 and conductance is higher, 100%, that temperature is called critical temperature. So many metals and some solid solution alloys that are mixture of two metals and some ceramics or intermetallic compounds may be example of superconductivity. So other examples of superconductivity are titanium, vanadium, zinc, tungsten, aluminium, mercury, and it could be mixture of niobium and titanium, or it could be mixture of lanthanum, strontium, and copper oxide, or copper nanotubes can also act as superconductors. So commercial applications for superconductors are superconducting magnets that are used for magnetic resonance imaging, that is known as MRI, or it could be used in NMR spectrophotometers. For above applications, conventional superconductors like in with mixture of niobium and titanium are used, and from these materials coils of these niobium titanium are prepared, which can produce higher magnetic field. So these superconductors are not too expensive, easy to use, and in this no heat loss may occur when during current flow. So other applications of superconductors that are related to magnetic properties is development of squids, and squids are superconducting quantum interference devices that are used for the detection of minute magnetic field. Very small or minute magnetic field can be detected from these squids. So which kind of material could be used for squids? These could be pure niobium or lead alloy with 10% gold or indium. So in this we can use pure niobium, or we can use lead that is lead alloy that is in which 10% gold or indium is mixed. So in other applications, smaller and lighter engines, generators, and some transformers that are used for electricity are other applications of superconductivity. And for example, superconducting motors that are used for ships and turbines. So these all are applications of superconductors. Students, this assignment is from your lecture that we discussed here. We discussed valence band and conduction band. You have to differentiate between valence band and conduction band. Some points that maybe we skip from here, you can find, you can search, and you can make a table in which you can differentiate between valence band and conduction band. That was our today's lecture. Thank you.